Martin, what is fractal geometry?
Well, fractal geometry has made some people very, very wealthy. Although, don't build your hopes up because the advantages might have been realized by now. But anyway, we all know, well, most people know about Euclidean geometry. It's the stuff you learn at school. There are four kinds of entities in, well, more than four, but four basic entities in Euclidean geometry. There's a point. A point has no dimensions. It doesn't have any width or height or breadth or anything. So that's a zero-dimension thing. A line is a one-dimensional thing. All you have to do is specify the length of a line and you've pretty well got it. So it's just one dimension. A plane, like the surface of a table or something, is two-dimensional. You need the width and the length. And finally, you have solids, like a cube, or some rectangular thing in 3 dimensions, where you need the height, the width, and the length. So that's 3 dimensions. The problem is that in nature, you never see straight lines. I mean, you might see approximations to them now and then, but you don't really see straight lines. You certainly don't see flat surfaces, and you don't see perfect 3-dimensional objects. So Euclidean geometry has determined the way that, for example, we design and build structures, because we understand it. But nature has no regard for Euclidean geometry. So a guy called Mandelbrot thought, well, is there a way to represent nature, the way nature does things? And he was the originator, really, of fractal geometry. I'll tell you what a fractal is in a moment. But you should know that he started with cotton prices. And what he found was that there are very small patterns in cotton prices that replicate on a big scale. So if you see a small pattern, you can predict to some extent what will happen in the future with the big pattern. And that's what he did. And it's, you know, that kind of theme that allows some people to make very large amounts of money on the stock market. They found these, it's called self-similarity, very small patterns that then emerge on a much larger scale. So the patterns are self-similar. They might be on a different scale, but it's the same kind of pattern. Now, what was needed was, just like we have 1, 2, 3 dimensions, was a dimension to measure nature. So, you know, the best example is a coastline. A coastline isn't a straight line. It isn't an area, it isn't a plane. So what is it? So various calculations have been devised to measure the number of dimensions in, for example, a coastline. And what you find is that Norway has, the coast outline of Norway has a dimension of 1.4. It's not one-dimensional, it's not two-dimensional, it's 1.4 dimensional. And the United Kingdom has a fractal dimension of 1.2. I think Canada is one of the lowest ones. I can't remember, probably 1.1 or something. Anyway, the calculation of these dimensions and the manipulation of them is horribly mathematical. You get into all kinds of things like measure theory and other things. So if you think you might want to have a go at the stock market, you're going to need PhD level mathematics. to find these self-similar patterns, the fractals, as they're called. And that's why it's called fractal geometry. You know, with a coastline, if you take one bit of the coastline, let's say you take a couple of miles of the coastline, you'll find patterns in there that are replicated on the scale of 100 or 200 miles. And the odd thing is, the shorter the measuring rod you use, the longer the coastline is, because of course you're measuring all the nooks and crannies. So this phenomenon has been seen in the way blood vessels branch, the way plants grow, all kinds of things like that. But it's still early days, and it's very complicated. My own intuition is that somebody needs to find something that simplifies it all. And then we can easily talk about 1.4 dimensions or 1.2 dimensions, instead of just the old Euclidean dimensions of 1, 2, or 3 dimensions. So that's what fractal geometry is. It's the geometry of nature, really. It's the geometry of things that replicate in a self-similar way. Tiny patterns then manifesting in bigger patterns, or you know, the bigger ones in smaller ones, and so on. So that's fractal geometry. It is used a lot now in biology, in physics, in well, just about all the sciences, to understand how nature does things, as opposed to imposing points, lines, planes and three-dimensional objects on nature. So it's early days, it has a long way to go, but if you can find some thing in fractal geometry with regard to the stock market that nobody else has found, it could be a way to making yourself $1 billion or $2 billion.